If you guys are in here for the Diagnosing Electrical Issues workshop, then you're in the right place. And I guess we can get started. Yeah. So, a little bit introduction to myself. My name is Rohan Nepomuceno. I am a senior, and I go to Davis Senior High School. I'm a member of this FRC Team 1678, and this is my 4th year on the team. I'm the hardware electrical lead, and in previous years, I've done Citrus Service, which is a program that we do on our team to help out teams to better themselves in order to get performing at the highest level that they can. And so I have a bit of experience dealing with a bit of electrical issues. Yeah, to start off, we'll start with the FRC control system overview. Most of you guys know the basics of how the robot works and moves. So the current iteration of the control system on the FRC side has been around since 2015, and it's been receiving incremental updates yearly in the case of the power distribution hub and the Rio 2.0. Yeah, we can just bring that in here. The main systems that usually have issues with them involve the signal, power, and pneumatic systems. But yeah, we'll start with the power system since every component on a robot needs power. So obviously the power system supplies electricity to all of our robot components, and all the power on a robot stems from the battery. And so we'll start from the battery. So the most common problems with the FRC lead acid batteries are strained and damaged terminal connections, degrading battery cell life, and signs of these problems could be low voltages, low ability to hold voltage, brownouts, and generally just not performing well with voltage drops and such. And also, if your batteries feel very warm, that is another sign that something may be incorrect with your batteries. And so a solution that we've been brought up to inform you guys about is trickle charging. So trickle charging is the practice of charging batteries equal to their discharge rate when they're at full capacity. So over time, batteries lose their charge rate and eventually discharge just by themselves because of the close vicinity of the chemicals inside of it. And so what happens is we'll charge it at the same rate that it's discharging when it's at full level, and it'll keep the health of the battery sustained. And also for terminal connections, what will happen is we've worked with another team, you might have heard them, 4414, who have, so we worked with them in getting a optimal design for, I guess, our battery terminal connections. So the pattern that we have is we use basically the standard FRC battery lugs connected to the terminals, and then on either side are a split washer, a and a Nord-Lock washer. Basically, a Nord-Lock washer is a washer that's made of 2 different plates that when when tightened together, it makes a really nice grip to the nut it's on, nut and screw it's on, and so it holds it pretty tight, and that avoids issues of connectivity and the issue of not having full contact. In previous years, if your battery terminal connections were a bit floppy, that was a really good sign that something is a bit off, because if they're floppy, that means they don't have full connection and they're not distributing charge fully. Next, we'll move to the main breaker. So the main breaker is connected to the voltage out side of your battery, or the red one. And so basically, that'll be between the battery and the rest of the power system. And so the main problems that we have with the main breaker include connectivity, because of the similar but not quite the same terminal lugs that we use on each side. So the signs of this happening again would be warm to the touch burn marks. I've seen burn marks in several robots before, and that's usually a good sign that something is getting very hot when it's not supposed to be. Voltage drops, once again, and complete loss of power. And also another sign of your main breaker might be a bit broken is if you cannot fully hear it click when it's latching in to distribute power, or when you cannot fully press the power off button on it, which releases the lever and switches it off. So if any of those components are loose, it most likely means that there's an internal damage on it. And so our solutions and remedies to these are back to the slide. So on the main breaker, they do give you insulation caps, which are woefully ineffective in covering the whole terminal. And so what we do is we insulate the power terminals with electrical tape fully around to cover all contact points of potential shorting. And so, yeah, the ones that are given are basically more ornamental than anything. And about the problem of a loose or very tight lever and button is it's often an internal hardware issue that cannot be quite repaired because of shearing in the metal inside the component itself. And so we often recommend that you guys hold a replacement main breaker if possible. But yeah. From the main breaker, we can continue on to the PDP, or the power distribution panel. And it's a big hotspot for electrical issues. The main problems that we see on the main breaker itself is the connection between the battery and the main breaker, port and gate connections being lackluster or poor, CAN issues, and broken fuses. But yeah, about connectivity. So it's similar situation to the main breaker in the sense that it's plate-to-plate contact. And so what we always recommend is insulating the outside wire to fully cover any spots of potential grounding or short-circuiting, and to routinely check on the bolts that are screwed into the PDP itself, the PDP terminals, as when your robot rattles around, things often get loose and such, so doing a routine check on those is really good. And understand the port layout. So the PDP itself has some notoriously strange gates and gate openings. So if you guys don't know, you just have to use a flathead screwdriver and kind of jam your way into the top section of the port. And so if you don't do it correctly, these thin metal plates often crack and are irreplaceable. So getting a better understanding of how the layout of the terminals work is really good, and often practicing and educating people on your team really helps because we've run into cases where someone inexperienced or a bit overconfident has come in and destroyed terminals, unfortunately. And fuses. So fuses, we like to think of as a feature and not a bug. So whenever you guys maybe you find that your power is cut out on your robot, and you check a fuse, if there's complete loss of power on that, it's usually the fuse being blown out. And so obviously it's wise to replace those, because they will not work if they are broken. But fuses are a good sign to another probably a worse underlying issue. And so fuses are the safety measures on the PDP to make sure that your whole PDP doesn't blow up. And so the fuse will blow up by itself. The power distribution hub is basically just a alternative to the PDP. It's made by Rev Robotics, and they use different gates and terminal connections. Some common problems we found with the PDH is frayed port connections, CAN issues, and broken fuses, once again. So with broken fuses, it's a similar situation. If they are blown out, replace them, and check what else you guys are working with, because you guys will most likely be in a bit of more of a pickle with that. And the frayed port connections. So due to the fact that the power distribution hub itself has different terminal connectors, they're more lever lock like or gate or basically like switch gates. So you have to crack them open and then put your wire in. And so what often happens is a wire gets caught on the side and it frays outward, leaving exposed copper on the outside. So I recommend that you guys double check what exactly is like, or what's frayed on your robot, and do routine checks to make sure that nothing's falling out of the gates of the PDH. But yeah. Oh, yeah. So the fuses will be, so a lot of them are see-through. So if what you can do is you can hold it up to a light possibly, and see that if so basically what a fuse is it's a thin metal piece that will basically break apart if there's too much load on it. And so what you can do is see, like, look through a light and see like whether it's still connected or not. So if the two like branches of it aren't connected, then it means it's blown up. But for the like more opaque and like the aluminum ones on the PDH, they're often like puffed up a little bit, or they're warm, and they're usually blackened on the ends from just the sheer amperage going through them and burning a little bit. But yeah. Yeah, so another thing you can use is the multimeter or an ohm meter. Not quite an ohm meter, but you can switch your multimeter to connectivity, and connectivity is just testing if it's continuous through this, if there's a circuit and it's continuous. So if you attach each side to it and it's doesn't say that it's continuous, then there's a break in there, and so it means it's been blown. But yeah, does that answer the question? All right. Yeah. So yeah, CAN. CAN stands for Control Area Network, and it is basically information and signal sent through nodes. Nodes are basically a receiver and transmitter on each CAN component, and so basically they'll be linked together to like send the signal throughout the robot. Some common problems we found with CAN are the poor connections, IDs, component IDs, and the CAN wire shorting out. So just a bit of a better explanation with what CAN is basically, as you guys can see here, it's like almost a chain link of nodes on the same line, and then a ground side, obviously. So what will happen is on the CAN loop, every component will receive the same information, but it's up to the component to read its ID and decode what it's basically being told by the RoboRio. And so basically they'll all receive like a big chunk of like signal, and they'll just read a certain section of it depending on what it's being told. And over there you can see it's a bit blocked by the robot, but yeah. But yeah, a CAN node is made up of the CAN transmitter or transceiver, sorry, the microcontroller itself and the CAN controller. So each CAN device has all these, and if there's a possible break, you might have to replace it on one of these. So when there's no CAN signal being received, what you can do is check continuity and connectivity. So basically what will happen is you check if like the link chain that that the CAN loop is still continuous. So you can basically break apart your CAN loop into two sections and check each side if it's continuous. And so what we recommend is if you guys find a CAN issue or a CAN break, then you should divide your robot into two halves and then test connectivity on one side and test connectivity on the other side. What that'll do is it'll tell you which half of your robot has the CAN discontinuity. And once you know which side it is, you'll divide in half once more and once more until you reach the area that you have a discontinuity. And so that's a really like effective way to finding the discontinuity. But yeah, even like certain components, it might be just one component to itself, which is a case for like maybe just repairing that component. Also checking resistance between components. If there's too high of a resistance on your CAN loop, then what will often happen is signals will get just dropped or totally like just oh yeah. Yeah, okay. So resistance in the CAN loop can come from basically a lot. Some of the more common things we found is soldering connections, bad crimping jobs, or just like exposed wire that is touching maybe like the frame. So what we recommend is testing each connection to see how much resistance there is throughout the whole CAN loop. Anywhere between like 0 ohms of resistance to maybe like upwards of 5 are very safe and often don't like lead to problems in the robot. So testing a resistance throughout your whole CAN loop can also tell you where there's points of high resistance and often where you'll find difficulty in your CAN loop. And we often like to check if the CAN loop is connected to the frame of the robot, because if it's connecting to the frame itself, then it's grounding out to itself, and CAN signal will not be transferred to the next component. So the way you do that is you connect a multimeter and check for voltage between 2 points of your robot. If there's voltage on your frame itself, that is bad. And so what we'll often do is turn off or remove power from one section of the robot, similar to how we did with CAN, and then test each side individually, and then divide it in half once again, and then divide it in half once again, until we find the point of like grounding to the frame. Another reason the CAN won't go through your robot components is often the IDs aren't set correctly. So if you like know a little bit about software, if two robot components are have the same ID or have no ID, they will not receive information from the CAN loop, and also testing the terminating resistor on the PDP. So on the PDP itself, there is a terminating resistor option, which you can turn on and off, or enable on and off. And so if it's not supposed to be on, that'll lead to basically your CAN loop running short. And if it needs to be on and it's not, it'll lead to the CAN loop basically just breaking because there's no terminating resistor at the end. And another reason that there might just be no CAN signal is a fried component. So oftentimes when components are plugged in to power incorrectly, they will just fry. And so once that happens, make sure to test if the CAN loop is still working, test if the component still turns on, and if you find out that you've fried your component, then unfortunately the CAN loop cannot pass through it. But yeah. For fuzzy or inconsistent CAN, there might be temporary discontinuity. So on moving parts, when things move, it might be like removing the CAN loop with it and then reattaching it as it moves around. So that's on like parts of the robot which are jostling and like anchoring points. And so like it's good to keep in mind that you're not working on a kinetic like statue of a robot. It's a robot and it's going to be moving around quite a bit. So securing your connections to like a stable place on your robot is definitely recommended. And another case on why fuzzy or inconsistent CAN might be happening is because of electromagnetic field disruptions. If you guys know anything about electrical theory, if you guys coil around a lot of wire and send current through it, it'll create an electromagnetic field, and it will affect other parts of your robot. So if you have like large coils of wire on your CAN, it's recommended that you avoid it because they might be disrupting your normal CAN signals. And also another thing with large wire coils is they add a lot more resistance due to the length of the wire. So basically, stay clear from large coils of wire, especially around your CAN signal systems. All right. Any questions before that about the CAN loop? Yeah. Okay, so yeah, it would be good if you test it and it still has continuity. But the terminating resistor should be at least 120 ohms of resistance. That's to basically just reground your CAN loop for more signal to be passing through it later. But yeah, 120 plus is good for standard terminating resistor, and the PDP and PDH both have one built in on the robot or on the component itself. So if you just flip that on, it should be good, and that will be the end of your CAN loop. But yeah. All right. So continue on, we'll be covering the Robo Rio. It is the central processor of the robot. It's like the brain. And the most common types of issues we find on the Robo Rio itself is power issues, CAN issues, port connections, and processing issues. But yeah, we'll start with power. So on the Robo Rio, it has an input of 7 volts to 16 volts. So that is the range that it will function at. If it's more, you risk danger of frying the part, and any lower, you risk it not fully functioning at its full capacity. And so when the voltage actually drops below around 4.5 volts to 6.8 volts, the Robo Rio will enter a brownout mode. So the brownout mode, it's not very legible here, but basically when it reaches this brownout mode, processing will be decreased. Basically all forms of processing will be severely hindered, and things will start to basically die on you. Signals will get dropped and such, and it's generally not good. So keeping a sustainable voltage like supply to your Robo Rio is definitely one of the most important things on your robot. And another thing that has had a lot of issues is the polarity of the voltage in. So on the Robo Rio, as you can see, the power in. So it's very good to keep in mind. So they have labels voltage and current, or VNC. And so just remember that the top V is for the red wire or the voltage in, and the C is for current out. But yeah, if you accidentally switch those, you risk frying the Robo Rio. So it's very important to keep it keep it in the right orientation. There is a chance that the Robo Rio does have a Schottky diode to prevent or to basically protect the Robo Rio from dying instantly if you reverse polarity it. But still generally not good to reverse polarity. Signs of port connections are basically just no power to sensors or not receiving signal. And so like on the PWM or the DIO ports per se, if you're not receiving voltage from there or you're not receiving signals back, it's wise to check the voltage out on those. And you can do that with an ohmmeter or a voltmeter, I guess. And what we recommend to make sure that there's full connectivity to your sensors is to literally like just hot glue them in. There's a 3D printable part that you can print out to basically like hold in all your connections into the ports of the Robo Rio, but I might have to do more research on that. The Robo Rio. So the Robo Rio has signal lights on the right side of it at the top corner, and so basically, the signals. Well, okay, I'll read them out. But green, good. That means whatever status light you're looking at, it is functioning properly. Red means there's either a fault detected in the connection itself, or it's not receiving enough power. And yellow means that there is a possible brownout detection, so it senses that something might be wrong. And so basically what you're shooting for is green, and you can test the power by taking out a voltmeter and testing points on your robot. If there's lag or dropping code on your Robo Rio, it's a processing problem. And so what we do to remedy that is we often shift processing out of our Robo Rio and onto separate components. And that will include like extension processors, which include the Canifier and PiPico. So what the Canifier is basically a little microprocessor that uses CanFD, and it basically like takes a little bit of the processing load off of the Robo Rio and computes it in the Canifier. And so yeah, the Canifier is connected to the Robo Rio through USB, and it uses CanFD. So CanFD is basically a better enhanced version of CAN itself. It's not been released how exactly it works, but it's quite useful for large processing on robots. So if you have a lot of stuff in the CAN loop, it definitely relieves the Robo Rio. And the PiPico is another processor that we use, a microprocessor that we use on our robot. We use it for more simple tasks, such as translating inputs from a sensor and such, and putting it into our Robo Rio directly. And so it doesn't have to translate it on the Rio itself. And so we connect that to the MXP port through an expansion board, and I'll get more into that later. Connected to the Robo Rio is the radio. It's basically what sends radio to your driver station, and it goes from driver station to robot to driver station, input output type thing. And so common problems that we find on the radio itself are power and the switch ports. So to remedy the power problem, we recommend not only having a radio power injector or a radio power module to inject power into the Ethernet and into the radio, but we also recommend maybe having a barrel jack to supply power directly through the barrel jack port on the left side, and so that'll just connect to 12 volts into the radio itself. Well, in practice, we found that the radio power module, so the thing on the right, right here, is more consistent than a PoE injector, the orange Ethernet cable that kind of looks like a Y, that goes into your the radio itself. And as for switch port problems, sometimes the Ethernet ports on the radio itself are just really loose and like don't hold the Ethernet itself in properly. And so what we recommend is, once again, hot gluing it down, or like maybe even zip tying it down. It doesn't have to be pretty, it just has to work. And checking the Ethernet switch power. So on the switch, it basically just lets you have more ports on the radio itself. And so what we recommend is making sure that's hooked up as properly as the radio itself. Crimson connectors. So everything in our robot is connected through Crimson connectors, obviously. Some of the ones that we use on our team, and we found that have been the most consistent, have been the Anderson power pole crimps. On the top left is the Anderson crimps that are required by first on your battery, they're pretty reliable. There's a reason they chose them. And so the Anderson crimps on those are basically pretty good. We've seen variants of it, but they just don't quite work the same. And so we recommend the standard FRC Anderson crimps. Anderson crimps basically envelop a whole like area of style of crimps, and so in the bottom right, on the bottom right corner, there's also Anderson crimps. They're pretty common for power, and we use them only for power exclusively. And so what we found is, so since they come in pairs of 2 usually, and can form into blocks, they're really useful for large scale routing on the robot. And since they, we also encourage the use of the through-hole connectors for the ports of each Anderson. So they're basically a bridge that goes on the 2 holes on each side of the connection and basically lock it in together. There's also 3 printable connector connections, which basically hold together the connections really tight. But when we're in a pinch, we often just use zip ties. They work perfectly fine. And moving on to our ferrule crimps. So we use our ferrule crimps for gate connections. So that'll be ports on the PCM, ports on the PDP and such, and basically all the CAN ports have similar gates. So I'll use ferrules on those. And so what ferrules are is basically these guys. So what they do is they turn your stranded wire basically into a solid core wire by gathering them all into one cylinder, and then when you crimp it down, it basically acts as a solid mass. And so it'll reduce fraying at the ports, and it'll reduce like little scraggly hairs of copper from being like outside the ports itself, and possibly running into problems with that. We also use the Molex connectors for our PWM or signal wires. We also use these for CAN loop. They're basically locking pin and socket crimps that go into housings that are also locking, and so they're a lot smaller, and so that we use them for the smaller gauges of wire. And since they're so fragile, we like to 3D print a connector connection piece, which basically holds each side of the connection really tight together. When we're in a pinch, or we need a prototype or a simple repair, we use lever locks, which is the top right. Lever locks are basically just like little gates with a copper plate inside. So what will happen is you flip up the lever, put in whatever wire you need, click down, and it's locked in. And it'll transfer power through the conductive plate, which the wire touches. So yeah, you just strip it, and then open it up, and then close it down, and it'll basically make a really quick, really simple connection. And so yeah, we've been using this. These are actually a recent development on our team, and so we've been using them for about a year, a little less than. But we definitely recommend it for competitions, because in the heat of the moment, it's very stressful to like focus on crimping and getting it right and getting it perfect. And so having the ease of access of a lever lock is really, really useful. Soldering. So soldering is a great way to connect wires if it's done correctly. There's a lot that can go wrong with soldering, and a lot of problems that we found with soldering is poor connectivity, melted or burned insulation, and shear force snapping, like during cases of cold soldering. And so what we recommend is there's a lot of training that can go through it, but what I recommend is to not cold solder. So cold soldering is when you solder 2 wires together, and the only thing that's holding them together is the solder itself. Usually wires themselves should be at least having surface-to-surface contact with solder in the middle of it to ensure a nice connection. And so what we recommend is if it can't pass a pull test, then it's probably a faulty or a poor grade connection. And when soldering, it's very easy to burn or melt the insulation, especially at higher temperatures. So what we recommend is keeping your soldering iron between between the temperatures of somewhere around 550 degrees. Just to it gives you that area of temperature gives you enough ease to melt solder itself, and heat up the wire, but to not burn insulation. And because insulation burning on your wire increases a ton of resistance, so what we do is have our newer students basically train for very long periods of time to make sure that they get it right, and doing constant resistance checks, and then once they get it down, to ensure that the soldering connection isn't getting damaged further, we would heat shrink wrap them to make sure that they're both weatherproof to anything that can go on the robot, to basically protect them. The pneumatic systems. So the pneumatic systems controls the airflow on the robot, and so it's a great way to get power into your moving components, but there's a lot of problems that can come with it, including leaks, which cannot show up digitally, as it is an analog form of movement, I guess, and a lot of power issues. So there's a lot of power issues with the pressure switch and the solenoids themselves. But yeah, we'll get into that. So the pneumatic control module is basically the brain of the pneumatic system, and common problems with that is not setting the right voltage out on your solenoid connections. So on the PCM itself, you have the option to select 12 volts or 24 volts of power and signal out to your solenoids. And if you do not set it to the right one, your robot or the solenoids will either not receive enough power or completely fry. So what you can do is check on the solenoid itself. It should usually say on the side 12 volt DC or 24 volt DC, and that'll let you know how much power supply needs to be going to your solenoids. And there are two different kinds of solenoids, double action and single action. So solenoids themselves, on each side of them, will have power if it's double, and only one side if it's single. Double action solenoids actually take up 2 ports on the PCM itself, and so you just gotta be wary of how much ports you're using at a time. And another problem we find a lot with the pneumatic control module is CAN. So make sure to do connectivity issues or connectivity checks and resistance checks as you work with the pneumatic control module. Pressure switches. So pressure switches detect the pressure on your robot, and basically at a certain point when it detects a high enough pressure, it'll let the PCM know that it's reached its limit. And so on the blue ports of the PCM, it'll read pressure switch. So as you can see, they're both colored blue, and that is because the pressure switch itself is dipolar, and so it doesn't matter which port you put either way, since the same result will happen on either side. But yeah, it takes its own specialized port basically. And common problems we found is with the pressure switch itself is it reading incorrect pressures. And so on a lot of pressure switches, they're actually variable. So what you can do is, it depends on what model you're using, but oftentimes it'll be, you can use a wrench to adjust the pressure at which it will send out basically a little signal to the PCM. But if not, you should check the product order product details to see at what pressure your pressure switch like basically like sends signal out. Um, and like yeah, it's a lot of getting it correct. And if you guys need a reminder, you can only have 120 psi action on your robot and 60 sword. So keeping that in mind when you're ordering a pressure switch itself. Air leaks. Air leaks are very common on pneumatic systems, and they're undetectable through your software. So the best you can do is listen to your pneumatic system. What we like to do is power off the robot and hook up a compressor or compressed air to one of the sides and to basically let air through the whole system and basically just key into what we're listening to as the leaks are coming out. Another sign that you might have a leak in your pneumatic system is the pressure gauges like shifting, or like the dials will be fluctuating. And this can happen because, or air leaks can happen because there's a poor connection between the tubes itself, including metal. Brass often needs Teflon tape in its threaded connections and such. So be sure to check your metal connections and use Teflon tape. Teflon tape is super useful, and it creates an airtight seal. And another reason you might be having a leak is because there might just be a straight up puncture in one of the tubes. And so what we do is do a kind of a CAN system check on it by splitting the pneumatic system into two, testing each side, testing the other side, and then going from there and working out where it's originated from. Any part on the pneumatic system can have leaks. Even solenoids themselves may have leaks, and those might have adjusting meters on them. But it's just a lot of checking, and sometimes you just have to replace a lot of tubing. Another thing we like to do with our tubing is to make sure that we're making flush, clean cuts on our tube. If you have like slanted cut and you put it into a port, it will not hold the pressure and it'll often leak out because it's just the ports are meant for a clean flush cut to have a lot of airtight seal on them. So yeah, like checking all those is really important to make sure that you have a working pneumatic system. For the pneumatic control module, they'll have a similar signal or status lights. Sorry, they'll have similar status lights to most CAN components on your robot. Green good basically means it's working all fine. But red means either no CAN connection, no compressing voltage out, or no solenoid power out or voltage out. And so what you can do is check the voltage at the ports themselves to see if there's voltage going out or not. But yeah, it's a lot of testing, and if you're not seeing any of the signal lights, it just means you're not receiving power. So testing the power connections on those are pretty important in order to have a working pneumatic system. We love organization on our team. We've been pushing to have our wires a lot more organized. And so a big part of our organization is labeling and diagrams. So what we do is before our robot is even put together, we'll have diagrams of a layout that we're looking to achieve. So we'll plan out what ports will be used for what, where they'll go to, what they'll connect to, and basically have a full map planned out before we start wiring. Obviously, a big part of the organization is routinely checking your wires, your pneumatics, your signal, your power, and such, and making sure that there's protection on your wires. So a really good way to protect your wires is with a sheathing or conduit. Sheathing is basically like the almost fabric-like wraps that you can put on your wires, while conduit is basically rigid or more rigid plastic, like snake like little sections that you can wrap around your wires, or you can put your wires through in order to give them more rigid movement patterns. Um, for organization's sake, we love working with design software to basically like collaborate on what the idea of our electrical system will look like, and to make sure that the IDs are all correct and that the belly pan layout is all correct. It just makes it a lot easier for them to identify what to put where, and for software, it makes it a lot easier for them to know what they're coding. So yeah, it's a big help. Continuing on with organization, we like to do wire layering. So we actually layer our wires in a certain configuration in order to achieve like a clean outlook. And so we often put power wires on the bottom, closest to the frame, because they're the most important and vital wires to our robot. And so when they're closer to the frame, they're out of the way of getting damaged by anything, and they're on a rigid structure, so they're not moving around too much. For CAN wires, we like to layer that on top of the power wires. We like the CAN wires to be layered on top, so they're a bit easier to trace, so we can see where the CAN connections are going. And so it just makes it really easy to know what's going to where. And we like to layer our pneumatics on top of that afterwards, simply because pneumatics are a bit bulky. So to put them on the bottom, they usually have to sacrifice either space or the pneumatics themselves by creating really tight bends on the pneumatics, which is pretty bad since air is flowing through them. And if you have a choke in your pneumatics, things don't flow well. What I recommend is that at like most 90-degree bends, anything more than like a 90-degree bend, things will usually get strained, and often cords will get cut due to the tension of like being on an angle of like maybe a metal part. And so we like to keep them pretty safe with that. And to keep in mind wire tensioning. So on our belly pan, we like to keep our tension and slack really tight, because we don't want stuff moving there. So whenever our robot gets bumped, our wires aren't jostling around and possibly getting damaged. And so we like to make sure that there's a lot of tension on the belly pan itself to make sure that they're secured. But too high of tension on parts like moving parts will lead to wires often getting snapped as there's too much tension. So we like to give a fair bit of slack on moving components, and anchoring wires to the like the point of rotation. And so, for example, for like maybe like a rotating arm, we would wire to the point of rotation and then up the arm, instead of having maybe wires just cut straight over to the arm itself, and when it moves, it'll break the wire. And just keeping in mind that this is a robot, it's not static wiring. We're not wiring a house. We're wiring something that moves around, like what I said earlier. But yeah, just keep like having that mentality that you're wiring up a robot that will go through a lot of movement and not optimal movement. But like keeping that in mind that your robot's health is based on your wire's health, and so you want to keep that pretty high. As for sensors, systems of the robots are like usually very fragile components on our robot. They're usually a lot tinier. They're usually very sensitive to like blunt force, I guess. For an example of this is our beam brakes and our color sensor. Our beam brakes are notoriously pretty fragile. If they hit a little bit, they'll just lose power completely. They'll not input, or they're not output. They will not output power either. They won't sense anything. And our color sensor is very fragile in light. So what we do for our color sensor is there's a light on the color sensor already, but what we like to do is basically supply with more light, because it's more light means more light for it to receive, which is more signal for it to receive, which is better data for us. And so like basically giving it that outlet to basically reach its capacity and see more helps a lot, and it's helped us with issues of not detecting a color of the ball, or not detecting a ball at all, which is a bit of an issue. And oftentimes, it's since they're so fragile, even in shipping, like sensors will get damaged. So unfortunately, sometimes you just have to replace a component, um, like just send it back to the manufacturer and such. But yeah. Expansion boards. So as I was talking about earlier with the Pi Pico, so we use an expansion board on our Robo Rio. And so expansion boards are basically anything that hook up to the MXP, the MXP port of our Robo Rio. It's like the thick middle of rectangular area of the Robo Rio. And so we found that it's a really good way to relieve the processing from the Robo Rio. And so we actually used an expansion board on our color sensor this year because we found that if you plug the color sensor into the I2C port, it completely like fried itself. It just like couldn't process the I2C. I2C is notoriously like a bit difficult to code, especially in FRC. And so to reroute the color sensing signal away from our I2C port and into our into the MXP port made it very very easy and very possible for our robot to detect color on our basically in our games. And yeah, it's basically just a super good way to like avoid the problematic areas of the Robo Rio, like the I2C. And miscellaneous stuff that like just like random stuff that happens on the robot is usually like grounding to frame, power grounding to the frame is really bad. That's like having a battery, but your whole robot's a battery. And so what we like to do for that is testing voltage once more, and often unplugging the battery because we don't want people like testing stuff while the robot is basically a super large battery. Again, routine electrical checks, pull tests are great. Checking your pneumatic system with compressed air, testing your pneumatic system with air, and then using compressed air to just clean your robot, especially this year with the fuzz of the cargo. We had a lot of dirty components with a lot of kind of grimy fuzz, and so like just going in there with compressed air is a really good way to basically just get all that dust and grime out there. For the more fragile parts like for the Robo Rio, what will happen is we'll often crack them open, and compressed air like just shoot out all the gunk and grime from the Robo Rio in order to clean it and to make sure it's not like getting shorted on something that could be easily avoided. So in the case of like cleaning components, what we like to do a lot for like when we're drilling on a robot, and there's electrical components present, we like to often like cover the whole electrical area with like maybe a rag or two, or like maybe a towel, just to make sure that there's no wood pieces, metal chips, or anything getting into the ports of our robot, because they're really sensitive, and we don't want burning wood, burning plastic, burning anything. We don't want burning stuff on our robot. And yeah, working with members of software to diagnose problems is incredibly important. When you're working with electronics, being able to have the status of your component be read out by a software member is incredibly useful, and will often lead you to the source of your problem a lot faster. And so it's just super useful to collaborate with the teammates that do the software on your robot, yes. And then finally, returning merchandise authorization, or RMA, is just returning your components sometimes. It's a bit unfortunate that sometimes just when you receive components, they don't work 100% of the time, but that's the reality of it. And so, like, especially with sensors and stuff, like being able to return them is just kind of it's a bit of a hassle, but it happens. Nothing's 100% confirmed to work on the robot, so it's unfortunate, but yeah. All right, that is the end of my presentation. Once again, my name is Rohan, and yeah. Is there any questions before we wrap up? No questions? All right, then thank you so much.